Problem A3. A volume Vf of a fluid with a uniform charge density ρ is spread into a room, forming spherical drops. As they float around the room, the drops may break apart into small drops or coalesce into large ones. Suppose that all of the drops have radius r, big R. Ignore interdrop forces and assume that V much larger than r cube. This problem consists of four consequent questions. Question A. Calculate the electrostatic potential energy of a single drop. So, if we have a drop with a radius small r with a uniform density ρ, we can count what is potential energy of this electrostatic forces in this drop. So, if this drop has radius r, we can calculate what is potential on the surface of this drop. That will be P equal 1 over 4 pi epsilon 0 Q over R. Now, what is charge Q? Charge Q, that's volume multiplied by charge density ρ. So that will be 4 over 3 pi r cube ρ over 4 pi epsilon 0 r, or that will be 1/3 1 over epsilon 0 r square ρ. This is our potential on the surface of this drop. Now, if we want to increase the radius of this drop by a spherical shell with a thickness dr, small dr, we need to bring this shell from infinity to this surface. So the total charge of this shell will be Q dq. That will be surface area multiplied by dr and multiplied by ρ. And to count how much energy we need to spend to bring this charge from infinity to the surface of this shell, we just write this equation: du equal 1 over 4 pi epsilon 0 charge this one, which is 1/3 1 over epsilon 0, I mean potential, I'm sorry. So total energy will be d U equal potential multiplied by charge, which is 1/3 1 over epsilon 0 r square ρ multiplied by 4 pi r square ρ dr. And now to calculate what is total energy of this sphere with a big radius, we just need to do integral from this function from 0 to big R. So that will be total potential energy. So that's equal 4 over 3 pi 1 over epsilon 0 r rho square r power 4 dr integral from 0 to r, which is equal 4 over 15 pi 1 over epsilon 0 rho square r power 5. So this is the answer for the first question A. So we can write it here: 4 over 15 1 over epsilon 0 pi rho square and r power 5. Question B. What is the total electrostatic energy of the drops? Your answer to question B should indicate that the total energy increases with the radius r. In the absence of a surface tension, then the fluid would break apart into infinitesimally small drops. Suppose, however, that the fluid has a surface tension gamma. This value is the potential energy per unit surface area, as in and is positive. So if we have total energy for one drop is this one, we need to count how many drops do we have. So number of drops n could be calculated by division total volume over volume of one drop, which is V final over 4 pi over 3 multiplied by r cube. And now total energy E equal number of these drops, V final over 4 pi over 3 r cube multiplied by this energy 4 over 15 1 over epsilon 0 pi rho square r power 5. And now we can subtract things, and finally answer will be r square rho square over 5 epsilon 0 multiplied by total volume. And here we can write this answer: r square rho square over 5 epsilon 0 multiplied by V final. So we see that total energy will increase if we increase radius. Next question, question C. What is the total energy of the drops due to surface tension? We know that the surface energy of surface tension is equal to area multiplied by this coefficient gamma. So we have total energy for one drop equal 4 pi r square multiplied by gamma. And now we have number of drops is n equal V fluid divided by 4 over 3 pi r cube, and the total energy, so it's equal 4 pi r square gamma multiplied by V fluid over 4 over 3 pi r cube. So that's equal to 3 gamma over radius multiplied by V final. So we see that energy decrease with the increasing of this radius of one drop, and we can write this answer here. Answer for C will be here, 3 gamma over R V final. And the last question is D. What is the equilibrium radius of the drops? We know that the total potential energy of electric forces and surface tension will be U total equal R square rho square over 5 epsilon 0 plus 3 gamma over R multiplied by V final. So to find what is our minimum potential energy, so this is the our condition for to find what is radius. Radius could be reached with a minimum of potential energy, total potential energy, because this function is increasing to infinity with the increasing of r, and this is decreasing to 0. So if we combine these two functions, we can find what is minimum. So for that we need to find what is derivative from U total by radius, which is 2 over 5 r rho square over epsilon 0 minus 3 gamma over r square multiplied by V fluid. And now we need to equalize it to 0 to find what is our radius. So the 0 for this expression will be for r cube equal 15 gamma epsilon 0 over 2 rho square, and radius, so radius will be just root, this will be root 3 1/3 of this expression. So this is the answer. Radius equal 15 gamma epsilon 0 over 2 rho square power 1/3. So this is the end of this problem A3.